Now that we know something about magnetism in general, it's time for us to now look quite carefully at magnetic nuclei and first ask this basic question: what is it that makes some nuclei magnetic and others non-magnetic? And in order to introduce this, I do need to remind you of one term you learned way back in Gen Chem, isotopes. And the most common ones that we run across quite often, and I'll use these as my example, are carbon-12 and carbon-13. Two isotopes of carbon, they differ by one neutron in the nucleus. So remember the basic symbolism. Carbon-12, usually symbolized with the 12 as a superscript in front of the element symbol. The superscript of 12 is the mass number, the number of protons plus the number of neutrons. Carbon is element 6 on the periodic table, so it has 6 protons, 6 electrons, and 6 neutrons. 6 plus 6 equaling 12. Carbon-13, carbon again, so it must have 6 protons, 6 electrons, but now this one has 7 neutrons to give the 6 plus 7 equals 13. Now, chemically, remember, isotopes are identical to each other. What any chemical reaction carbon-12 does, carbon-13 will do. But nuclear properties, they are very different nuclei. We don't normally think about the various isotopes often in chemistry, because remember, in chemistry, it's the interaction of the electrons, the electron clouds that we're most focused on. And these two versions of carbon have the same electron structure. But when we do nuclear magnetic resonance spectroscopy, the differences in these two nuclei become very important for us. And for carbon, interestingly enough, carbon-12 is a non-magnetic nucleus, whereas carbon-13 is a magnetic nucleus. Whenever we do a carbon spectrum in NMR, it's actually the carbon-13s we're looking at, not the carbon-12s. It's an indication that we have something similar to what happens with the electrons. Remember, electrons are charged particles. They are spinning. Each electron spin can generate a magnetic field, but most matter is non-magnetic because those electrons are spin paired. Something similar must be going on in the nucleus as well. For a carbon-12 nucleus with 6 protons, if they're all spin paired, 6 neutrons, they're all spin paired. Carbon-12 is a non-magnetic nucleus, even though it too is built from spinning charged particles. That odd electron or odd neutron in carbon-13, 6 protons, 7 neutrons, 6 protons spin paired, 6 neutrons spin paired, but that one extra neutron is enough to make the carbon-13 nucleus magnetic. In fact, as a general rule of thumb, if you ever run across a nucleus of whatever atom that has an even number of protons and an even number of neutrons, like a carbon-12, it's going to be a non-magnetic nucleus. If you run across a nucleus and any isotope of that nucleus that has an odd number of protons, or an odd number of neutrons, or an odd number of both, there's a high probability that that is going to be a magnetic nucleus. Carbon-13 is a good example of that. Quantum mechanically, we keep track of nuclear magnetism in the various nuclei by assigning a spin quantum number, I equals 1/2, to every unpaired spin we find in that nucleus. We're going to say then that carbon-13, with that one odd neutron in there, is a spin 1/2 nucleus. The most common nucleus we study in NMR spectroscopy is the nucleus of the hydrogen atom. Odd number of protons, just 1. No neutrons at all, so it is an unpaired proton there. It is a magnetic nucleus. It's kind of interesting to realize that every hydrogen and every molecule we ever study is magnetic. It is generating a magnetic field. It's a weak magnetic field, but we can detect it and we can make use of it. It is a spin 1/2 nucleus. Hydrogen 2, also called deuterium, the heavy isotope of hydrogen, 1 proton, 1 neutron. It has an odd number of both, and each contributes a spin of 1/2. Overall, then, if we add them together, we say deuterium is a spin 1 nucleus. It is magnetic, but with a spin quantum number higher than 1/2, it is going to be a somewhat more complex magnetism than we see in just the simple hydrogen 1 nucleus. There are other nuclei that we study in NMR that are magnetic. Another one that you could think about is nitrogen and its two isotopes, nitrogen 14, nitrogen 15. At first glance, you might think nitrogen 14, with that nice, happy, even number up there, is going to be a non-magnetic nucleus. But remember, nitrogen is element 7 of the periodic table, meaning that mass number of 14 is built from 7 protons and therefore 7 neutrons, an odd number of both. It's actually a magnetic nucleus with a spin quantum number of 1, 1/2 for the odd proton, 1/2 for the odd neutron. The other isotope of nitrogen that you can study by NMR sometimes is nitrogen 15. It's much rarer than nitrogen 14. It has 7 protons, 8 neutrons. It's a spin 1/2 nucleus. It's not as cut and dried and straightforward as I may have implied here, and so as a simple example, consider boron 11. Boron is the 5th element of the periodic table, so there are 5 protons and therefore 6 neutrons in a boron 11 nucleus, but magnetically it is a spin 3/2 nucleus, implying that there are actually 3 unpaired spins in that nucleus. For reasons I really can't tell you why, 2 of those particles that you might think would be spin paired are actually not spin paired in a boron 11 nucleus. We collect a lot of this information in tables of magnetic nuclei and their spin quantum numbers, and here's an example of one now. And you can see that a lot of the various nuclei, there are spin 1/2, spin 1, cobalt goes all the way to spin 7/2. There's a wide variety of these magnetic nuclei out there. If you ever run across a nucleus that has a spin quantum number greater than 1/2, like deuterium or hydrogen 2 or like boron 11, we collectively give them a name. They are called quadrupolar nuclei, and it's basically going to mean that their magnetism is not as simple as we might first think it is. It's going to be somewhat complex and oftentimes difficult to work with, a topic we'll dig deeper into later on. A nice graphic that kind of summarizes a lot of this information comes from the University of Utah, and basically it's a periodic table of the various magnetic nuclei, and a copy of these is available on the course website for download as well. This particular table looks at or shows only the spin 1/2 nuclei, the simplest magnetic nuclei. And if you look at this table carefully, you'll notice there's not that many of them. Hydrogen is there, the carbon-13 isotope of carbon is there, and there are others, but there's not really that many, unfortunately, for us NMR spectroscopists. If you then look at this table, it's the same type of periodic table, but this one simply shows all of the quadrupolar nuclei, all of those with complex magnetism, spin quantum numbers at 1 or greater. You can see there's quite a few quite greater number of these out there, and some of these you can do NMR on readily. Others are very difficult to do or virtually impossible to do. And so these are not the ideal nuclei that we look at in NMR spectroscopy. And in fact, thinking about an ideal nucleus, when we do NMR spectroscopy, the ideal nucleus has essentially 3 criteria that it has to meet. It has to be abundant. There has to be a lot of them out there. A spin 1/2 gives us the most straightforward and simplest spectra to look at, and it must be universal. And I'll come back to that phrase in just a moment. For all of those criteria, hydrogen, the nucleus of the hydrogen atom, is by far the most ideal. Hydrogen 1, the simple hydrogen isotope, is 99.9% and greater abundant, spin 1/2, and hydrogen is universal. It's found in almost every kind of compound we chemists want to study. Carbon-13, on the other hand, it is spin 1/2, and let's face it, it's carbon. It's the very definition of universal. But it is not abundant. Remember, only 1% of our carbon atoms are C13. 99% of them are carbon-12s. As far as NMR is concerned, frankly, 99% of the carbons out there are worthless. And so that makes carbon-13 NMR a challenge. It's not impossible. You've seen some examples of it already, and you'll see plenty more. But it does mean that compared to hydrogen NMR, carbon-13 is a greater challenge to the NMR spectroscopist. There are other nuclei out there that are nice to look at. Fluorine-19, for example, is 100% abundant, and it's spin 1/2, but it's not a universal element. If you're a fluorine chemist, you live and die by NMR. It's a great technique, but fluorine is not found in all kinds of different compounds. It's a much more restricted element than some of the others. Phosphorus-31 is another good example. 100% abundant, spin 1/2 nucleus, and highly useful to some areas of biochemistry and even inorganic and organometallic chemistry. But again, it's not a universal element found in all kinds of different chemical compounds. If there's one element that's a great challenge in NMR, it's actually oxygen. In fact, if I were in charge, I would like to have an abundant spin 1/2 nucleus of oxygen. But if you'll notice, there are no spin 1/2 nuclei of oxygen, abundant or otherwise. We cannot do NMR readily on oxygen. Any of the magnetic nuclei that do exist are quadrupolar and very rare. We can measure the effects of oxygen on the atoms that are around them, but we can't detect by NMR oxygen atoms directly. NMR is essentially blind to being able to directly see oxygen atoms, which is unfortunate. It's just the way it is, I guess. From here we go on now and consider a little more quantitatively some numbers associated with how we talk about and measure strength of the magnetic fields by nuclei and the frequencies of light we need to manipulate these magnetic nuclei.